My name is Kyle Hecker, and this is portfolio number 2 for Fluids 307. The first conceptual question is, what is a Moody chart, and when can it be applied to non-circular pipes? The answer to this question is a Moody chart relates the Darcy-Weisbach fanning friction factor to Reynolds number and surface roughness for flow in a circular pipe, but it can be applied to non-circular pipes if that diameter is replaced by the hydraulic diameter. So this is the difference between a non-circular and a circular pipe for a Moody diagram. So then the calculation question for this part of the project is a fluid flowing through a pipe of 1 centimeter diameter that's 12 meters long, open to an atmosphere of 5 atm. This also means that the stream is also at 5 atm. If the velocity of the fluid is 21 meters per second, and the density of the fluid is 1,100 kilograms per meter cubed, with a viscosity of 0.31, what is the absolute pressure just before it exits? So, we go through the K-FAPS method and write down all of our knowns. We are finding the absolute pressure. We are assuming incompressible flow and a steady state, and then these are the properties we have listed in the problem. We have a way to find volumetric flow rate and an equation for area. So we find our area of our pipe, our volumetric flow rate, which turns out to be this number. Then we plug it back into this, which volumetric flow rate can relate to our pressure. We solve this equation for pressure and get a pressure of around 25,000 kPa. Then we convert the ATM to kPa, and we're able to solve for an absolute pressure. What this does assume, though, is that the pressure drop will be a negative number, which is obviously not possible because you can't have a negative pressure, and so the fluid will just not flow if this was related to real life. The second question is conceptual question number 6. For required and net head, there is a change in volumetric flow rate for a given pumping system. How can this be possible? So for the answer to this is a required net head increases with volumetric flow rate, and available net head decreases with volumetric flow rate. That is how this answer is able to relate to this question. So the calculation question states, a tornado comes ripping through Nebraska and tears through one of the many cornfields that are there. One of the many pieces of corn, just a single kernel, not like a whole cob, is thrown into the air. If it has a diameter of 2 centimeters and a density of 470 and is able to be thrown 300 meters into the air, how long will it take for it to come down if the air pressure is 1 atm and it is 15 degrees Celsius during this storm? And you are able to assume that the kernel acts like a sphere. So the known values are written down, and then we're looking for the time. So what we're able to assume is the Reynolds number is small, which is able to let us state that Stokes' law is applicable, and then the terminal velocity is negligible. The properties from 1 atm and 15 degrees Celsius are the density and the viscosity, and these come from table A15. So then we're able to solve. This is the equations are able to force due to drag and force of buoyancy, and you can expand these equations into these terms, and then you can solve for velocity, and then you're able to cancel out when your velocity is solved for, and it minimizes to this. You plug these numbers in, and you get a velocity of 55,671. Then distance equal to rate times time, and then the distance, because we're going up and down 300 meters, is 600 meters over 5,600, and we're able to get 0.1057. So this kernel is moving extremely fast. Conceptual question number 7 states, explain the Euler turbo-machine equation and how shaft work is implemented in this equation. So the T shaft for the Euler turbo-machine equation is equal to density times volumetric flow rate of radius times velocity out minus radius times velocity in. So shaft torque is equal to the change in momentum from inlet to outlet. So this can be related to the equations for momentum. The calculation question states water is flowing down Mount Kilimanjaro and passes through a cylindrical pipe full of rocks, as shown in this figure below. This is just not drawn to scale, but it's just to help to see what is kind of going on. The entrance is 2 meters wide, and the rocks are 50 centimeters in diameter, and the pipe is 8 meters long. If the porosity of the rocks is 47%, and is initially 1 meter of water in the bottom of the pipe, that's what this little black line down here is for. At high season, what will the flow rate of water off of Mount Kilimanjaro be? So we write down our knowns that were stated in the problem. We're looking for the flow rate off of the mountain. We're able to assume the pressure drop and kinetic energy is 0. We're assuming this is 25 degrees Celsius, and then it is incompressible and steady state for flow. They were given us properties in the problem. So we start with the Bernoulli balance. We're able to cancel out our pressure terms and our velocity terms as those both equal 0. And we can solve for this friction factor. We get a friction factor of 88.29 when 9 meters is implemented for z. And then we're able to use that number to solve for velocity. After plugging it into this equation, velocity comes out to be very high, 14,353, which means the flow rate will also be very high at 45,092. This number is also not realistic, but it states a good way to show how flow rate can be calculated for a bed or a permeable bed idea based on this problem. The final problem is the conceptual question states, how is Rayleigh flow defined and why is it unitless? So the answer to this is Rayleigh flow is an ideal gas flow with constant specific heat flowing through a constant area duct with heat transfer but negligible friction. It is important because this flow can be thought of when thinking about choked flow and Mach numbers, supersonic, subsonic, all of these numbers. This is the equation for Rayleigh flow. And then these are all of these units mean. So the volumetric dilating coefficient is B, that is unitless. Then you have temperature T in Kelvin, G is gravity, D is distance, V is viscosity, and A is the thermal diffusivity. And it has these units, which all cancel out. So the question is, a very strong volcano exploded and the atmosphere can now be thought of as full of helium. The stagnation pressure and temperature are 1200 kPa and 400 degrees Celsius. This blast is very powerful and killed everybody within a 150-mile radius. The condition... So these conditions pass through a turbine, and this turbine can be thought of as a turbine in industry, where the outlet pressure is 1500 kPa. If gamma is equal to 1.667, Cp is 5.193, and R is 2.077, and the process is isentropic, what is the power per unit mass? So we go through our kFAPs, write down our knowns. We're looking for W over m dot. We're able to use our assumptions, and then we can state our properties given in the problem. Solving this equation, we use this T equation to solve for T2 using our gammas and our pressures. T2 comes out to be 736 Kelvin. We then use the first law, and we're able to cancel out all these things because of steady state, adiabatic, no kinetic energy, and there's no change in elevation. And then we're able to use the correlation between H out minus H in is equal to Cp T2 minus T1. Plug that all in and get a work per unit mass of 326.46 kilojoules per kilogram. Finally, the appendix, which states the differences made from the original IQEs to this portfolio. So, for the first question, the calculation question was redefined to have the system or the stream also at 5 atm, and it was explained that the fluid was not moving after the pressure drop was negative. The sixth question was the calculation question had a better explanation as to what was being thrown, the kernel of corn, not the whole cob. Question 7, the concept question was provided with more clarity on the inlet and outlet terms, and the calculation question more assumptions added, and y terms could be canceled. And finally, the concept question was explained for number 8 upon as to what the importance of Rayleigh flow was.